Hey Kaylee, your audio's on, which is fine, but just want to let you know. Someone's audio's on, which is also not a problem. Just want to let you guys know. Let's see. Let's wait a minute here. Pin my video. And the attendance link. 1 second. There's the link to the attendance. Harold, I think you might have some noise coming through because you're unmuted. Started in just a minute here. I forgot I can mute people. So there we go. That's a little bit better. Super cute picture, Allison. I love the little mouse. It's great. I think that's a mouse anyway, right? Looks like a mouse, yeah. All right. Where are we at here? Lots of things. So I watched Sanders' last class. He's talking about hamster. Okay. Cute little hamster. It could be a mouse, but yeah, it's definitely a hamster. Sanders is talking about lots of things, talking about derivatives. We should probably talk about derivatives. And I'm looking at his current homework as well. There are definitely lots of derivative questions on there. So yeah, we can definitely do some, let's do some stuff. And I've got a whole list with that list here. Let's see. No. His homework is pretty confusing. Yeah, I would agree. Some of it's not terrible, some of it is kind of terrible, but we'll parse that out and figure it out. I just want to see. There's a couple things I wanted to mention before we started looking at his homework. So just a few things he has talked about in class that are definitely going to be important moving forward. So rules to be aware of when it comes to derivatives. So derivative rules. All right, I think this pen is trash, maybe. We'll leave it over here to one of those bright ones. So some rules we have for derivatives. If your function is x to some power, then the derivative is n times x to the n minus 1 power. It's called the power rule. We use it a lot. Oh, sorry, let me fix my, I know you guys have a problem, but my video is currently mirrored and it looks all wrong to me. 1 second. There we go. All right, so we have the power rule. So for example, if your function is say like x to the 7th, then your derivative is 7 times x to the 6th. And this one's better than that one. I'm trying to go through all my pens and get rid of the trash ones. We can also see something like, if your function is 2x to the 8th minus 9x cubed plus 4 over x squared. Well, before differentiating that, I would probably rewrite it so that this was a power, or x to a power instead of over x to some power. I'd probably rewrite this as g of x equal to 2x to the 8th minus 9x cubed plus 4x to the negative 2nd. And then we can differentiate that and get g prime of x. 8 times 2 is 16x to the 7th minus 3 times 9 is 27x squared. And then minus 2 times 4 is minus 8x to the negative 2 minus 1 is minus 3. So if we can write things as just powers of x, we can differentiate them very easily. But there are, of course, other functions that he has talked about. Let's see, this pen is okay. He talked about sine and cosine. So he showed you guys in class that the derivative of sine of x is equal to cosine of x. And while it's nice to show the proof, he definitely did it, it's perfectly fine. I think there's a better way to see this that's more useful for us. So I'm going to graph sine of x. Yeah, let's do it here. So sine of x is a period of 2 pi. And at 0, sine is equal to 0. Pi over 2, sine is equal to 1. At pi, sine is equal to 0. At 3 pi over 2, sine is equal to negative 1. And at 2 pi, sine is equal to 0 again. So the sine graph looks like this. And it repeats. And hopefully you guys can see that all right. So now, let me close this, sorry. What I'm going to do is I'm going to graph the derivative. So I'm going to remind you guys, the derivative as a function is just the slope of the tangent line. So I'm actually going to look at these 4 points. Sorry, 5 points. And ask you what the slope of the tangent line is. So specifically, let's get out a red pen here. So this is where I want to use the other red pens. I'm trying to use old, too many pens. I'm trying to use the garbage pens over here to write on top of the other pen because like it gets all messy. So let me ask you this. Right here at pi over 2, what's the tangent line? Or what I should say, what's the slope of the tangent line? Well, that's a horizontal line. So what's the slope? It's, sorry, my hair's holding my eyes. Ugh. So the slope here is 0. And in a similar way, right here, we have a horizontal tangent line, and the slope there would also be 0. And then at this point here, that tangent line looks like the slope could be 1. Same deal over here. The tangent line looks like it could have a slope of 1. And here, it looks like the slope could be negative 1. So here's what I'm going to do. I'm going to graph those points where the y values are now the slopes. So if I say, okay, here I'm going to say my slope is 1, so I'm going to get a y value of 1. And this is a common method for graphing the derivative of something. You look at the slopes of what the tangent lines would be, and say, I'm going to graph those values. So the slope is 1, I'm going to get a y value of 1. The slope is 0, I'm going to get a y value of 0. The slope is negative 1, I'm going to get a y value of negative 1. Slope is 0, y value of 0. Slope is positive 1, y value of positive 1. And look, if I look at the graph of this, that's exactly the graph of cosine of x. So I can see that if this is y equal to sine of x, then y prime, the derivative, is exactly cosine of x. And while not super rigorous, this is a good way of seeing, oh yeah, the derivative of sine is actually cosine. In a similar way, we can show that the derivative of cosine is actually negative sine. So I do the same sort of thing. If I had more room, I would just, I could probably draw it down here. It's going to be a little bit tight. So if I do the same sort of thing. So like now the slope of the tangent line. So everybody, I would like someone to answer, what's the slope of the tangent line here? You guys there? Anybody? Sure, I can repeat the question. So I'm asking, if I look at this graph here, what would the slope of the tangent line be? Exactly. Thank you. Appreciate it. It would be 0 because the tangent line would be a horizontal line. And a horizontal line has a slope of 0. Here, the slope would be negative 1 because it's going down from left to right. Here, the slope of the tangent line would be 0 because, again, it's a horizontal line. Here, the slope of the tangent line would be positive 1. And here, the slope of the tangent line would again be 0. If you look at this, It looks exactly like the sine function, but flipped over. So it looks like, oh, the derivative of cosine, or the second derivative of sine, is negative sine. So we have kind of this nice cycle of derivatives of sine and cosine. So if my function is sine of x, the first derivative is cosine of x. The second derivative is negative sine of x. The third derivative, so if I take the derivative of negative sine, well, the negative one I can just think of as a constant multiple. This pen is looking like it's hard to see. You're trash. The third derivative is going to be negative 1 times the derivative of sine, which is negative cosine. And finally, the fourth derivative, well, the derivative of negative cosine is negative times the derivative of cosine, which is negative sine, which is just sine of x. So for any sine or cosine, if you do 4 derivatives, you get back to where you start. So the fourth derivative of sine is sine. The fourth derivative of cosine is cosine. The fourth derivative of negative sine is negative sine. All of the sine and cosine functions, whether they're positive or negative, cycle through back to themselves after 4 derivatives. So that actually helps us answer a question like question, what is it? There was one on there, like question 2 from the homework. So I could ask you a question like, if my function is cosine of x, what's the 95th derivative of cosine of x? Well, here's what I really need to know. How many multiples of 4 are in there? And then what's left over? So what's 95 divided by 4? Well, 95 divided by 4. 4 goes into 95, 2 8, subtract 1, 5, 4 goes into 15 3 times. Subtract 2, the remainder of 3. So here's what I'm really thinking. 4 goes into 95 23 times, has a remainder of 3. So I could do the fourth derivative 23 times over. I could do 4 derivatives and 4 derivatives and 4 derivatives and 4 derivatives, and that would get me back to cosine of x. So I could do, if I take out the biggest multiple of 4, which is 92, this is going to be equal to the third derivative. So here's what I want to make really, really clear. The 95th derivative of cosine is the same as the third derivative of cosine. Just like the first derivative of sine would be the same as the fifth derivative of sine, because every 4 derivatives you get back to where you start. So the 95th derivative of cosine is the same as the third derivative of cosine, and we can find the third derivative of cosine. The third derivative of cosine is first derivative, second derivative, third derivative, sine of x. So we can answer a question like that not too difficultly. I like using a slightly different notation. I think it makes it easier to see what's going on there. Let me write another question in a similar way. Let's say I want to find, so I'm going to use the Leibniz notation. So I want to find the 101st derivative, so d101 over dx to the 101 of sine of x. Here's what I'm actually going to do. I'm going to think of it as a multiple of 4 and whatever's left over. I know 100 is a multiple of 4, right? 100 is 25 times 4. So I'm going to break this apart as the 100 derivatives and then the leftover 1 derivative. So I'm going to think of this as 1 derivative and then 100 derivatives. Okay. So let me ask you guys a question. What's the 100th derivative of sine of x? It is definitely sine of x, because every 4 derivatives, you just get back to where you started. So this multiple of 4 derivatives is going to get you back to sine. So this is going to get me back to the derivative of the 100th derivative of sine of x is just sine of x. And then the first derivative of sine of x is just cosine of x. This is definitely how he intends for you to do problem 2. He intends you to take out the biggest multiple of 4. That's not going to change anything. And then whatever's left over as a remainder, that's how you find the actual thing he's asking you for. All right. Yeah. Let's also talk briefly about the product and the chain quotient rule. So the product rule. So we need the product rule to be able to take derivatives of things that aren't just powers of x. Like if I want to find, or sine, if I want to find the derivative of like x cubed times cosine of x, I need the product rule. There's no other way to do this. So he just kind of told you guys, no, I think he derived it out. So here is the product rule. If you're taking the derivative of a product, f times g, it's equal to f prime g plus f g prime. Or as I like to think of it, oh, by the way, here's the attendance form again. I always think of the product rule, it's the derivative of one part times the not derivative of the other part, plus, and then you switch it, and you do the not derivative of the first part times the derivative of the second part. So it's always one derivative and one not derivative multiplied together, and then you add the two pieces together. And we can kind of see this, right? If I was going to take the derivative of, say, like x cubed times x squared, which we should know, right? It's just the derivative of x to the fifth, which should be 5x to the fourth. But if I was pretending like I didn't know the product rule for a second, I could do this the wrong way. Say, and so actually the point of this is to show you guys that you can't just take the derivative of each part. If I did this as the derivative of x cubed is 3x squared, and the derivative of x squared is 2x, if I multiply those together, I get 6 times x cubed, which is not the same as that. So this is wrong. It's not right to just take the derivative of two pieces that are multiplied together and multiply the answers together. We have to use the product rule. So here's how the product rule would actually help us do this problem. Instead of just simplifying, you say, okay, well, the product rule says I take the derivative of one piece, I'm going to do the derivative of x cubed. I'm going to leave the other piece alone. Plus, then I'm going to do the other thing, right? I'm going to leave the x cubed alone and multiply by the derivative of the second piece. And that's going to look like, so the derivative of x cubed is 3x squared times x squared plus x cubed times the derivative of x squared is 2x. And this ends up being 3x squared times x squared is 3x to the fourth. X cubed times 2x is 2x to the fourth. And if you add this together, you get 5x to the fourth. Just like you should for the product rule. Or should for this derivative, right? This derivative is 5x to the fourth. And the product rule also shows that. So then we can use the product rule here and say, okay, well, the derivative of x cubed times cosine x is the derivative of x cubed times cosine of x plus x cubed times the derivative of cosine of x. And that's just going to be 3x squared times cosine of x plus x cubed times the derivative of cosine is negative sine of x. And I might rewrite this as 3x squared cosine of x minus x cubed sine of x. So that's one example of the product rule. And then it can get more confusing. So we could ask a question similar to problem 3 on the homework. Something like, for f of x equal to x to the fourth times sine of x, what's the second derivative? Well, to find the second derivative of a function, how does x, so it's not that x cubed equals 3x squared, it's that the derivative, right? That's what this little prime symbol means here. The derivative of x cubed is equal to 3x squared. Hopefully that clarifies that question. So for this one, we're going to do the same sort of thing. Before we can find the second derivative, we have to find the first derivative. So to find the first derivative, we're going to use the product rule. And again, I'm just going to write it out the usual way. So it's the derivative of x to the fourth. So I'm going to write x to the fourth prime, which we know is going to be 4x cubed. That's just the power rule, times the other thing left alone, plus then we're going to do the opposite, or the vice versa, as I just say, right? We do derivative of one thing, we do the other thing alone, and then we flip it. We do leave this alone times the derivative of that. And I'm actually going to find those derivatives. So this first derivative here is equal to 4x cubed times sine of x plus x to the fourth times the derivative of sine of x is cosine of x. Are there questions about that? Okay, so then to find the second derivative, we're just going to take the derivative of the derivative. Now here's the thing. This derivative has two products, right? This product and this product. So I'm going to use the product rule for this piece and add and use the product rule for this piece. So here's how it's going to look. So I'm going to think of this is one piece, 4x cubed times sine of x, and then this is x to the fourth times cosine of x. So taking the derivative here, let's see, so I'm going to get the derivative of 4x cubed times sine of x left alone plus 4x cubed, so 3, times the derivative of sine of x. And then we're going to do the same thing over here. Derivative of x to the fourth times cosine of x plus x to the fourth times the derivative of cosine of x. And then we just find the derivatives. So the derivative of 4x cubed is going to be 12x squared, and then times sine of x. Leave that alone. 4x, the derivative of sine is cosine. So you get 4x cubed times cosine of x. Here the derivative of x to the fourth is 4x cubed, so I get 4x cubed times cosine of x. And then I get x to the fourth times the derivative of cosine, which is negative sine of x. A lot of the time, if you can see that the derivative of something is going to be a negative, we often put that out in the front here. Sure, I can definitely explain how to do this. So from right here, from here to here, or further back. Sure. So all I'm doing, so here's what I should say, right? So here's what I'm thinking. So I'm thinking of this here as, like, usually people use u and v. So that's my u and that's my v. And to take the derivative of u times v, I'm using the product rule. I'm getting u prime times v, 4x cubed derivative times sine of x, plus u, which is 4x cubed, not derivative, times v prime. So I use the product rule for that part. But then I also have to do the product rule for this other part here, because I have x to the fourth times cosine of x. So for this piece here, and let's call these h and g, the product rule is going to be, we kind of have room here, h prime times g, right? That's the derivative of the first part times the second part, plus h times g prime, first part times the derivative of the second part. So I'm just using the product rule for each of the two things that are being added together. And then after we write it all out like this, we just take the derivative. So the derivative of 4x cubed is 12x squared. The derivative of sine x is cosine x. The derivative of x to the fourth is 4x cubed. The derivative of cosine x is negative sine x. And then I might do one more simplification, especially since this here and this here are the same. So I might write this as 12x squared sine of x plus 4x cubed cosine plus 4x cubed cosine is 8x cubed cosine of x. And I would write this as minus x to the fourth times sine of x. That's not super duper important. Excuse me. So those are some product rule examples. Again, you're always doing the derivative of one part times the not derivative of the other part and then switching it. And there's always a plus sign in when you ever have a product rule, right? You're always adding the two pieces together. Okay. The quotient rule is very similar in nature to the product rule. It's just a little bit different. And I'll tell you how I think about it. And then we'll look at some examples. So here's the product rule again, just for comparison. So the product rule says that the derivative of the product, f times g, is f prime g plus f g prime. Right, and really, right, we're using shorthand notation here. This is really the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. In a similar way, the quotient rule actually looks a lot the same. The quotient rule says that if you have the derivative of the quotient f divided by g, the derivative is f prime g minus f g prime. So far, almost exactly the same as the product rule, except we're subtracting instead of adding. But then you divide by the denominator squared. Some people use a mnemonic device to remember this. They say low d high minus high d low over low squared. That's another example. So you can say low d high minus high d low all over low squared, where the low is the g, right? Low is g, and the high function is the f, right? Low, high. And d means take the derivative. So this is g times the derivative of f, which is exactly what I have here, minus f times the derivative of g, which is exactly what I have there, all over the bottom square. And honestly, the way I really say it in my head is I say it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. That's just how my brain actually thinks about it. So that's the quotient rule. You definitely should memorize both these rules. For the product rule, the order doesn't really matter as long as it's the derivative of one piece and the not derivative, right? You can add in any order, it doesn't matter, you can multiply in any order. So you could just as easily write this as g prime f plus g f prime, and that would be totally correct as well, because you're still getting g prime times f added to f prime times g. On the other hand, for the quotient rule, the order really does matter because the order of subtraction is important. You can't subtract things in opposite orders and get the same result, right? 7 minus 2 is not the same as 2 minus 7. They're actually negatives of each other. So make sure the quotient rule, you're always doing the bottom thing times the derivative of the top thing first, and then minus the top thing times the derivative of the bottom thing second, all over the bottom square. All right, let's look at an example. Yeah. So let's find the derivative of, say, f of x equal to x. Let me be super careful for 1 second. That should be fine. Yeah. X squared plus sine of x over cosine of x minus x. So let's find the derivative of this. And again, we're just going to use the quotient rule. And typically, I don't really try to simplify the quotient rule unless I have to. So here's my derivative. Here's how I'm going to write it out. It's the bottom. All of it times the derivative of the top. So I could write the derivative of x squared plus sine x, but I'd like to not write a ton of things. So I'm actually going to start just finding. So I'm going to say, oh, look, the derivative of the top is 2x plus cosine of x. Right? That's the derivative of x squared plus sine of x. Minus the top times the derivative of the bottom. The derivative of cosine x minus x is negative sine x minus 1. And that's your derivative of cosine x minus x. All divided by the denominator squared. And I will be very frank with you, I would not simplify this. I would leave this as it is unless I was specifically instructed to simplify this, because it's just gross to multiply it out. Now, here's the question I really wanted to ask. That's not super exciting, though, but fine. I want to find the equation of the line tangent to this function. I'm not going to write it out, it's this function, at x equal to 0. So, if you see this sort of question, which there's definitely questions 1 and 4 on your homework are questions of this nature. When you're ever asked to find the equation of a tangent line, you have to find two things. You have to find a point, meaning an xy coordinate pair. Well, we have x, we can probably find y. And we also need a slope. And the way you find the slope is by finding the derivative. So here's what we do. To find the slope, I need f prime at the point I'm interested in, which is 0. Right? If they said find the slope at 1, I would find f prime of 1. If they said find the slope at -3, I'd find f prime of -3. So to find the slope, I'm just taking my derivative, because the derivative is the slope of the tangent line at a point, and plugging in the point I want to know the slope at. I'm going to plug in 0, it's going to be kind of a mess. Cosine of 0, which is 1, minus 0, times, this is probably going to end up being 0, which is going to be lame, or well, or maybe not. 2 times 0 is 0, plus cosine of 0 is 1, minus 0 squared is 0, and sine of 0 is 0. And it doesn't really matter what this is if this is 0, but we can find it anyway. Sine of 0 is 0, so you get 0 minus 1. All divided by, hopefully not 0, cosine is -1 minus 0. Sorry, cosine of 0 is +1, excuse me. So looking at this, we end up with, let's see, 1 times 1 minus 0. So 1 on top and 1 on the bottom, which is 1. So our slope is 1. So whatever our point is, we can take the equation of our line is going to be y minus the y coordinate equal to 1 times x minus the x coordinate. Now I just have to find the x and the y coordinate. Now, this is probably not a super exciting example because we already know the x coordinate is 0. So our x1 is 0. And to find the y coordinate, you just plug it back into the original function. So the y coordinate, y1, is the original function evaluated at 0, which is going to be 0 plus 0 over 1 minus 0, which is just 0. So here's my not very exciting answer. I get y minus 0 equal to 1 times x minus 0, which is just y equal to x. So that's how you find the equation of the tangent line to this function at x equal to 0. Sure, let's do another example. Time is it? Okay. Let me think here for 1 second. More quotient rule stuff. Let's say our function is x cubed plus, let me think for a second. Sure. Let's say that's our function. It's x cubed plus 7 over x squared plus 1. And I want to find the equation of the tangent line to this function at x equal to 2. And so again, when you see this sort of question, when you see find the equation of the tangent line, you should be thinking, oh, I have to find a slope and I have to find a point. I've already got half of the point. Let's find the other half. So if x equals 2, y is going to equal f of 2, which is just, let's see, 2 cubed plus 7 over 2 squared plus 1. 8 plus 7 is 15. 4 plus 1 is 5. 15 divided by 5 is 3. So here's what I know so far. My equation is going to look like y minus 3 equals whatever my slope is times x minus 2. And our job now is just to find that slope. And the way we find the slope is by finding the derivative. So to find m, to find the slope, we're going to find the derivative as a function. All right, so we're not using the limit definition here, although we could use the limit definition. I mean, you shouldn't use the limit definition. You should definitely use the quotient rule. But what I'm trying to say is you will probably, oh no, he's not going to give you guys a midterm. I would say if you were having a midterm, you'd be asked to find the derivative using the limit definition. Since you're not, you probably shouldn't sweat it too much. But you should still know about the limit definition of the derivative. Okay, so to find the derivative here, again, quotient rule. Bottom times the derivative of the top. Right, the derivative of 7 is 0, the derivative of x cubed is 3x squared. Minus the top times the derivative of the bottom, which is 2x, all over the bottom squared. I do want to mention, just because I've seen it too many times not to, is I've definitely seen students write this without the parentheses. So if you write this without the parentheses, it's actually, most of the time it's wrong. And the reason it's wrong if you don't write these parentheses, which I will write back in a minute. So if you write it like this, x squared plus 1 times 3x squared and minus x cubed plus 7 times 2x, it looks like it's just the 1 times 3x squared, and it's just the 7 times 2x. But really it has to be all of the bottom times the derivative of the top, and all of the top times the derivative of the bottom. So you definitely need parentheses around anything that has more than one term. We could simplify this, but we don't really need to, because I'm just going to plug in 2. So f prime of 2, right? I'd rather just plug in 2 and simplify after. So plugging in 2, I get, let's see, 2 squared plus 1 is 5. 3 times 2 squared is 3 times 4, which is 12. Minus 2 cubed plus 7 is 8 plus 7, which is 15. Times 2 times 2. Oh, this is going to be fun. This is, wow. Somehow I picked something that's interesting. Oh, well, what happens? Sorry, if you plug in 2 here, you get 15 times 4, all over 2 squared plus 1, which is 4 plus 1 squared. And we end up getting 60 minus 60 on top, which is 0. So our slope happens to be 0 here, which is kind of atypical, but it can happen. If your slope is 0, that means your equation now is y minus 3 equals 0 times x minus 2. If 0 times anything is just 0, so our equation is really y minus 3 equals 0, or y equal to 3, which makes sense. Like if your tangent line has a 0 slope, it means you have a horizontal tangent line, and you should just have y equal to a constant. But typically, you probably would actually get something else. Yeah, that's kind of funky that this worked out that way. Oh well, I happened to pick a number that happened to do a thing. Okay, yeah, we really should move on. Ooh, there's 2 things to talk about still, at least there's 2 big things to talk about still. So he's briefly talked about how the derivative of e to the x is e to the x. It's definitely something to also know. So if I were going to say, I don't know, for, what's he writing here? Sure. So if I had like, you know, y equal to, sure, e to the t minus cosine of t over t squared, I could find, so you could find, I could write this as y prime, I could write it as dy dt. There's lots of different notations for the derivative. Try not to get too confused by them. In problem 6, he's definitely using this dy dt notation. It just means find the derivative. So again, we're going to use the quotient rule. We're going to get the bottom times the derivative of the top. Derivative of e to the t is e to the t. the derivative of minus cosine t was minus, the derivative of cosine is negative sign, so it's minus a minus sign, so it's plus sine of t. Minus, then we flip it around, we do, so we did the bottom times 0 to the top, now we're going to do the top, e to the t minus cosine of t, times the derivative of the bottom, which is 2t. All divided by the bottom squared. And again, I'm not big on simplifying, but we could simplify this, right? You could distribute this t squared. Well, actually, really what we should actually do is factor out a t. Right? There's a t squared here and there's a t there. You could factor out a t. And then you're left with a t times e to the t plus sine of t minus a 2 times e to the t minus cosine of t, right? The t went away because I factored it out, all over t to the 4th. And then you can cancel this t with one of those t's. And then you can distribute and get t e to the t plus t times sine of t minus 2e to the t. Sorry, my t's always look terrible. Plus 2 cosine of t all over t cubed. So that's how that would look. In the last almost 10 minutes we have, I do think we really should get to the chain rule because he definitely talked about that today. And problems 7, let's see, no problems. Problems 9 and 10 definitely have to do with the chain rule in your homework. We can definitely talk more about these problems on Friday, but we should certainly mention the chain rule here. And okay, so I'm going to try and do this quick. So the idea with the chain rule is that, sorry, my shoe's untied, I need to tie it, is that it allows you to take the derivative of a composition of functions. So here's what I want to do. How do I want to say this? I want to tie it. So I want to take the derivative of, like, say, x cubed plus 1 squared. And what I'm really going to do is I'm actually going to multiply it out before I take the derivative. So I'm going to get the derivative of, let's see, x cubed plus 1 squared is x to the 6th plus 2x cubed plus 1. And now we can take the derivative of that. And we're going to get the derivative of x to the 6th is 6x to the 5th. The derivative of 2x cubed is 6x squared. And the derivative of 1 is 0. And now I'm going to factor in kind of a weird way, actually. This is going to look maybe slightly strange. I know I can factor out a 6x squared, but I'm actually going to write it, well, I will do it that way first. If I factor out a 6x squared, I'm left with an x cubed plus 1. But I actually want to write this as 2. So I'm going to break up 6x squared as 2 times 3x squared. I'll write this as 2 times x cubed plus 1 to the 1st, even though I don't need that, I'm going to write it, times 3x squared. Now here's the idea of what we actually did. We said, oh, I've got the derivative of some function squared. And the derivative of that function squared, well, I know the derivative of x squared is 2x. The derivative of some function squared is 2 times my function to the 1st, just like the power rule kind of works, times the derivative of that function. Right? The derivative of x cubed plus 1 is 3x squared. And this is how the chain rule works. You basically take the derivative of the outer function, you leave the insides alone, and then you multiply by the derivative of the insides. Let me show you a more general example. So the reason that actually works is because of the product rule, right? If I took the derivative, and now you guys really should pay very close attention here. If I took the derivative of some function squared, it doesn't matter what the function is, it's just some function squared. But really, when you square something, you're just multiplying it by itself. And the derivative of the product, f times f, well, I can use the product rule. It's the derivative of the first thing times the second thing left alone, plus the first thing times the derivative of the second thing. But those are the same, right? F prime times f and f prime times f are the same thing. So I really have 2 times f prime. But I could really think of this as 2 times f to the first times the derivative of my f. So really, I'm using it's still the chain rule. I did the derivative of the outside function, so I got some stuff squared. The derivative was 2 times my stuff to the first, and then I had to multiply by the derivative of the inside stuff. If you prefer, I could use this longer notation here. I say it's the derivative of f of x squared, and it ends up equaling 2 times f of x to the first times f prime of x. And that's exactly an example of the chain rule, because you're taking the derivative of the outside function being something squared. The derivative of something squared is 2 times something to the first, and then we're multiplying by the derivative of the inside function. And this works actually for any power. So time is not my friend today. So there's this thing called the repeated product rule. If you have a product of more than 2 things, you can do a repeat product rule. So if I have the derivative of f times g times h, well, I can think of it as f times g times h, meaning it's the derivative of f, we'll leave the second piece alone, and then it's f times, take the derivative of the second piece. Let's take the derivative of g times h, I have to use the product rule. So I get f prime times g times h plus f times derivative of gh using the product rule is g prime h plus gh prime. And multiplying it all out, it's f prime gh plus f g prime h plus f g prime. So here's the thing about this. If you take the derivative of a product of 3 things, it kind of works out the way you might come to expect it to, which is you're going to get the derivative of one piece times the not derivatives of the other 2 pieces in each possible way. You get the derivative of f times the other 2 pieces, you get the derivative of g times the other 2 pieces, and you get the derivative of h times the other 2 pieces. And this actually is extendable to a product of any number of things. So if I took, and so bear with me, there is really a reason for this. If I did the derivative of f times g times h times j, I'm not going to bother actually proving it, but I'll just say it definitely ends up being f prime times g times h times j plus f times g prime times h times j plus f times g times h prime times j. My j's are looking stupid. Plus f times g times h times j prime. And so on and so forth. Now, there is a reason for this, and I want to show it to you. And then we'll probably be out of time. So, I want to find the derivative of f of x to the nth power. Because I want to be able to say, what's the derivative of, say, I don't know, x cubed plus x to the 70th power? I don't want to multiply that out, right? It's possible to multiply it out. I do not want to multiply it out. You don't want to multiply it out either. And here's the thing. The derivative of some stuff to the 70th power, well, I know the derivative of x to the 70th is 70 times x to the 69th. So the derivative of some stuff to the 70th power is 70 times my stuff to the 69th times the derivative of that stuff. Also, make sure you guys do fill out the attendance form in case you didn't already. I know we're out of time, but just let me finish this one thing and I'll let you guys go. You're, of course, welcome to go if you need to go. So here's the idea. I'm going to take the derivative. So the reason this works is because of the repeated product rule. And this is really the derivative of f times f times f times f a bunch of times, n times to be precise. Well, I'm going to take the repeated product rule says the derivative is the derivative of one piece times the other pieces in every possible way. So it's f prime times f times f times f. It's f times f prime times f times f times f. It's all the way to the last possible one where the last f is got the primes f times f times f times f prime. Okay, here's the real quick rundown. In each of these products, there are n things multiplied together. One of them is f prime, and the other n minus one of them are all f's. This is really f times f times f n minus one times, or f to the n minus one times f prime. But so is this. So are all of them. And since there are n different spots f prime could end up in, the first spot, the second spot, the third spot, or the last nth spot, there are n of these things. So this is equal to n times f to the n minus 1 times f prime. Or in our more usual notation, it's n times f of x to the n minus 1 times f prime of x. So here's the last word I want to leave you guys with today. When you take the derivative of some function to the nth power, it's n times that function to the n minus 1 power, like the power rule says it would be, but then you have to multiply the derivative of the inside. So the derivative of this function to the 70th power is, well, something to the 70th, the derivative is 70 times something to the 69th power, but then you have to multiply by the derivative of that inner function. And that's the essence of the chain rule. We will definitely talk more about it on Friday. So yeah, I'll see you guys then. Don't hesitate to send me questions, start a discussion, you know the drill, and please fill out the attendance form. I'll see you guys later.